Okay, so now we're starting our third chapter, functions. Now, a function is something that you're going to meet in programming. And although there's kind of an abstract thing written down here, the basics of a function is something that takes an input and produces an output. That's the basics of it, but we'll go through this slowly. So a function, which we write like this, so the idea is here, x are the inputs and y are where the outputs live, is a relation between inputs and outputs such that each element, each possible input appears in exactly one ordered pair. So that means that every single input has an output. And it says exactly one, so no input has two outputs. So each input appears in exactly one ordered pair. So each input is related to exactly one output, but different inputs can have the same output. Therefore, a function is a subset of x, Cartesian product of x and y, because it's sum of the ordered pairs such that every input appears once and only once. So here it says the crucial features are every element of x appears in an ordered pair, every input has an output, and every element x appears in only one ordered pair. No input has more than one output, and no input has no output. Every input has an output. If xy is in f, which is to write x is related to y by f, we can write that x is mapped to y. And you can also write y is equal to f of x. So f of x is notation for the output of the input x. So y is the image of x under f. There's all these different languages. The set x is known as the domain or the source, informally the inputs, and the set y is known as the codomain or the target, informally the outputs, or rather where the outputs live, because not everything in the codomain is actually an output. And the range is a subset of y that is contained in at least ordered pairs. So these you could think as y is where the outputs live. It's something like the ambient or universal set for the outputs, and the range is the set of outputs, which can be thought as the things that are hit by the function. Okay, as functions are relations, we can represent them using arrow diagrams. You normally would not use digraphs because often, see, you can't use a digraph if the input set and the output set are different, only if they're the same. And usually we won't do that. So usually we'll use arrow diagrams. So there'll be a number of elements we want in an arrow diagram. So we can represent the set of inputs, represent the set of outputs. You want to see a label, X for inputs, Y for outputs, and I'd like to see an arrow with a label saying that this is a function. And usually, so here for example, maybe you have 3 inputs and maybe 4 outputs. So let's say inputs 1, 2, 3, outputs say A, B, C, D, and maybe we have something like 1 is mapped to A, 2 is also mapped to A, and 3 is mapped to C. So this shows that every single input, so this is just an example of a function. We could write down it in terms of ordered pairs. 1 is mapped to A, 2 is mapped to A, and 3 is mapped to C. And this is a function because it's a relation between x and y, so it's a subset of ordered, it's a subset of x Cartesian product y, and every element of x, 1, 2, 3, appears in exactly one ordered pair. Okay, it's fine that 1 and 2 have the same output, that's fine, and it's fine that B and D are not hit. So the range here of f is equal to all the things that are hit A and C, and that is a subset of the codomain. Right. Sometimes a function can be specified by a rule or a formula, and the set of ordered pairs would look something like this. So we'd have maybe, there's different ways I can write this. So set of input x, output f of x, basically use the formula for the function as x ranges over all the possible inputs. So given an element of the domain x, say little x, the rule gives a way of finding the image of x under f. So this formula. Okay, let's see some examples. Now, people in this room doesn't really work. So let's take comp 1c, which is all the v people, union myself. That's going to be the people involved here. And I'm going to define a relation. So it's a subset of p times n. So remember, these are a person together with some number. Now I'll write the two notations just in case you're a little bit ahead. So I can write either person number in relation, which is the same as writing p is related to a number. These are just different notations for the same thing. If person P has age n. Okay. Now this is a function because every person in the room has an age. Everyone can be associated with an age, and no person has two ages. It's absolutely fine that 19 in the set of n occurs in more than one ordered pair. That's fine, and it's fine that some ages aren't hit. For example, 16 probably isn't hit. The domain is p. The p, well, we know what p is. All of you students, union myself. The codomain is n, and the range is not all of n, but the following subset. So the range of or is equal to all the ages. So well, let's say the set of ages of students as we go over comp 1c. So all your ages, 17, 18, 19, 20, 21. I assume we have all those and maybe a few older people. And we'll throw in myself. Now if none of you are 35, this union is unnecessary, but I'm 35. So they're all the things that are hit. Okay, so that's an example of a function. Age is a function. Let's see what we got here. So represented as an arrow diagram, each element P, each person is mapped to a single age. It is fine that different people can be mapped to the same age. And we're going to draw some kind of an arrow diagram here. So here's the set of people. And here's n. Now remember, n is, and we won't include 0, is 1, 2, 3, 4, 5, etc. No, just do dot, dot, dot. I'm assuming there's no 16-year-olds here, so we'll do 17, 18, 19, 20, 21, 22. We'll assume there's no 23-year-olds, we'll leave that out. And then myself there, 35. So, and of course this keeps on going. So we're talking 1, 2, dot, 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 17, 18, 19, 20, should have done 16, 21, 22, 23, dot, 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 35. Dot, 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 going on forever and ever and ever. So this is the codomain. And P, now we're going to say there's 40 students. So student 1, student 2, student 3, dot, dot, dot. We obviously won't list everyone. Student, say, 38, student 39, student 40, and myself. So let's say, that's what I want to do here. So the age function here, actually we've called it OR, which isn't a great name for it, but there we go. So let's say student 1 maybe, let's say, is 20. Student 2, let's say they're 18. Student 3, let's say they're 18 as well. Now all the other things would probably be hit, but okay, we haven't got enough of these. So student 38, let's say, is 22. Student 39, let's say, is 22. Student 40, let's say, is 19. And if you include all of the people, you'll probably hit a good few more ages, and myself is 35. So what's fine is that things aren't hit, and what's fine is that some ages here, like 18 and 22, are hit multiple times. This is fine. Okay, so this is an example of a function. So now I think we're going to see a non-example of a function. Let S be the set 1, 2, 3, and define a relation R on S by this. So remember, a relation R is a subset of S times S, so some ordered pairs. The first thing is in 1, 2, 3, and the second thing is in 1, 2, 3. And this is not a function. Now, Now, the best way to analyze your relations was to use a digraph, and your best way to analyze a function is to use an arrow diagram. So let's draw an arrow diagram. So here's the set S containing 1, 2, 3. Here's the set S containing 1, 2, 3. I want to get good labels on these. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. And this is we're calling this R, so we'll draw it there. And now let's draw the ordered pairs. So we got 1 is sent to 1. So this is an arrow diagram recommended to analyze functions. 1 is sent to 2, and 2 is sent to 3. So this is not a function, and there's two reasons why. So the first reason that it's not a function is 1 has 2 outputs. So not a function, why? So note that 1 has 2 outputs. So that's one reason. And 3 has no output. Now, funny enough, looking at it, if you did the inverse relation where you turn these around, it is a function. 1 is sent to 1, 2 is sent to 1, 3 is sent to 2, but we're dealing with this. We can also see it here. We can see that the input 1 appears twice and the input 3 does not appear, but it's easier to see it with the arrow diagram. Okay, so let's see another function. So let x be the set 1, 2, 3, 4 to find a function s from x to the natural numbers, where this is where we see an example of a rule or a formula to calculate the outputs. So if you give me an input x, the output is x squared. So it's input, for the input x, the output is x squared. So let me say that one more time. So what this formula means is if you give it an input x, the output is x squared. So let's write down the ordered pairs. So if we put in 1 as an input, we can calculate the output. So if you put 1 in, you get out 1 squared. 1 squared is 1 by 1 is 1. Now let's put in the input 2. So 2 in, the output is 2 squared. 2 by 2 is equal to 4. Let's put 3 in. And of course, we know this is a function, so like there's no sense of not putting in 4. Everything goes into this formula. Because we're saying it is a function. And like the thing about a formula is if you put in 3, like you'll always get out 3 squared, which is 9. You can't get out 1 and 2. So that's in a sense why a formula is a good example of a function. And finally put in 4 and we get out 60. Okay, so what is the domain? So the domain is the numbers that you put in. We'll probably draw an arrow diagram, or maybe there's no real point to put an arrow diagram here. So the domain is the inputs. X set 1, 2, 3, 4. The codomain is the place where the outputs live, and you can think of it as the ambient or the universal set of the outputs. So the outputs here naturally live in N, which consists of 1, 2, 3, ... going on forever and ever, and the range, which you write as range of S, is equal to just the outputs 1, 4, 9, 16. 1, 4, 9, 16. And it's absolutely fine that not everything is hit. Okay, very good. So there's a further remark here that isn't something that's going to be examined, and it kind of says maybe why, if you want to read it, why are functions so important? Now for you, functions are very important from the basically programming, but where the functions originally kind of came in, it came in from science and stuff. So if you want, you can have a read of that if you want. Okay, so here's some exercises on basics of functions. Right, next thing, graphs of functions. Now we've got a number of terminologies because we've got these arrow diagrams, digraphs. So these graphs, a graph of a function, we could call it a coordinate graph. Okay, a graph of a function consists of all the ordered pairs. So really, the graph of a function is actually just its set of ordered pairs. Now it can be infinite if you've got infinitely many inputs. And often though we can draw it, which is what this is getting at. Note that every function satisfies what's called the vertical line test. We'll probably see this later. A relation on or is a relation from or to or. Okay, so let's start. A relation on or is a relation from or to or. So this is a subset of or times or. And I think we've seen this in a previous lecture on Cartesian products. Or cross or is the plane. A 2D curve region shape is a subset of the plane. So a relation R. So what I'm saying here is if you've got the plane, two-dimensional space, and you draw a curve, a region, or a shape, all of these are subsets of the plane, and therefore they're actually all relations. And a function is a relation, so it is a subset of the plane. That means that we can actually draw a function essentially. It's certainly a function that the inputs are real numbers and the outputs are real numbers. And it'll be such that each element, okay, well, let's see. So we've got this so-called vertical line test. A graph is not the graph of a function if a vertical line intersects more or less than exactly once. Okay, let's see how this actually works. So what we're going to do is we're going to draw some kind of a curve here. Let's say something like that. Okay, and let's look at the points x equal to a1 and x equal to a2. So you've got some curve on the plane, and the question is it the graph of a function? And you can test it using something called the vertical line test. So let's draw these vertical lines. There's this one, and there's this one. Right, suppose that the line x equal to a1 does not intersect the graph, and the line x equal to a2 intersects the graph twice. So you can see 2 points. So what can we say about these points? Okay, so remember what you're going to have here is this is certainly a relation on or. So it's a set of sum is really just saying subset there, some ordered pairs. Where the first number is a real number and the second number is a real number, and using coordinates it means you just plot all the points. So for example, this point here is a certain x value and a certain y value. Okay, and you plot all such points. That's what a coordinate graph is. So let's think about this one anyway. So if this is supposed to be the graph of a function, what about ordered pairs of the form a1y? But because this line does not intersect with this, there is no point a1y in this graph. And remember, the coordinate graph of a relation is just all the ordered pairs. So that means that, say if f is just a relation, so there's no point like this. This basically means that there's no output for a1. So there's no point on the graph of the relation of the form a1y. So that means that there's no number y such that a1 is related to y. There's no number y such that a1 is mapped to y. So there's no output for a1. So if this happens, it's not a function. No output there. The relation above here, not a function. Okay, so that's the first thing. So if your vertical line does not intersect the curve, it's not a function. Now the other possibility is if it intersects more than once. So let's look at the coordinates here. So this is, say, A2, we'll call this Y1, and this we'll call A2, Y2. So this relation, which I'm going to call R now, well, I better call it F, I suppose. But that suggests it's a function, it's actually not. So we have A2, Y2, and actually we're going to draw pictures of these in terms of arrow diagrams. And A2, Y1 in F. Yeah, I think what we're going to have to do now is draw the arrow diagram for this. So this is set A, inputs. This is set B, outputs. Now, at the moment, all what F is a relation. And you can still draw a relation with an arrow diagram. And we're looking in particular at A1 and A2. So, and then in terms of the outputs, we're looking at Y1 and Y2. So the fact that this doesn't intersect with the curve means that there's no ordered pair of the form A1Y, so A1 is sent to nothing. So this input does not have an output, so that means that this thing is not a function, and that's the first thing. If we draw this one here, we see that A2 is actually sent to two different things, because we got A2 is sent to Y2, and we also have A2 sent to Y1. And remember, if you look back at your definition of a function, every input must have a unique, with respect to A2, it must have only one output. This has two outputs. So this means that A2 has two outputs. And so if you do a vertical line and it cuts the graph of the curve twice, then it's not a function. Not a function. Now, if it cuts it only once, then it has to be, because if every vertical line cuts it once, that means that every single input has an output, and if it cuts it only once, it has only one output, and that's exactly what a function is. Every input has a unique output. So that's the vertical line test, and I think that's pretty much everything we need here. Oh, we've got some examples. Good. Okay, so let S be the set 1, 2, 3, and define a relation or an S by 1, 3, 1, 2, 2, 2. We can represent this graphically as a network graph. When I say graph, I mean coordinate graph. So we'll do all three just so we see all three of them. So the network would be, will actually be a directed network. In other words, a digraph. Yeah, you see, we've got issues with the terminology. So I want to say this is a coordinate graph. Because if we say graph alone, then it's like it's either a directed or undirected network, and a directed network. Okay. So let's draw it as a network. So as a network, our digraph, 1, 2, 3. What do we got? We got 1 is related to 3. 1 is related to 2. Now we can only do this because it's relation on S. It's hoping to be a function from S to S. 1 is related to 2, and 2 is related to 2. So that's this relation represented as a digraph. We can also do it as a coordinate graph. 1 along the X, 3 along the Y, 1 along the X, 2 along the Y, and 2 along the X, 2 along the Y. And do not join the dots. And an arrow diagram. So the labeling is important here. I want S, S, and the name of this mapping, as it were, is R. So we have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And let's join them up. 1 is sent to 3, 1 is sent to 2, and finally 2 is sent to 2. Okay. So what about it? Well, it's probably hard to see that it isn't a function here. It's easiest here. If you draw the horizontal line, or excuse me, the vertical line here, it fails the vertical line test because it cuts it twice. So it's not a function there, and also it's not a function there, because this vertical line, it must cut it once and only once. And that it cuts the graph once here doesn't really matter. It has to always cut it exactly once, no matter where you draw it. Now you might ask, what if I draw it in between, but they're not possible inputs. You can also see it's not a function here because 1 has 2 outputs and 3 has none. Okay, here we go. Is the following the graph of a function? No. And there's 2 reasons we can say. If I draw a vertical line, say at x equal to 0.2, or x equal to, say, minus whatever, 0.4, so this cuts twice. So this is to say that 0.2 has 2 outputs. That's not a function. And minus 0.4, because it doesn't intersect, has no output. It's not the graph. This is the graph of a relation, but it's not the graph of a function. And I think that's everything for functions here so far.